Okay, hello, this is additional video on chapter 9. I hope you can also working with me. So you can start with 9.7, 9.8. I think both of these questions just looking at on the table, and then you can use Hash law and you can find the heat of reaction. Okay, I think it's pretty simple, and I think from this two questions, you can have more familiarity with the heat of reactions. At least try to read the table B1 first, okay? But I would like to start with the 9.14. So we will have this normal heptane that is dehydrolyzed to toluene and hydrogen. So this is heptane, and this is the toluene and hydrogen. And we have these reactions. And we all have the information on the temperature at the beginning, and then it operates isothermal, so it's a constant temperature, and then the reaction will goes to completion, so it finish up until the end. So average heat capacity, so we already have heat capacity. We take this as our heat capacity. First, draw the flowchart, and then enthalpy table, and then required heat transfer. What is the heat of heptane dehydrolyzation reactions at 400 Celsius and 1 atmosphere? So actually, this fourth question is basically our standard procedure in looking at the reactions, okay, and then looking on how the enthalpy will be calculated. Okay, so it's actually pretty similar with chapter 7 and 8, but the difference is now we have another terms that we call the heat of reactions. Okay, so I hope you are already familiar with chapter 8 at least, okay, to see that we are going to evaluate the enthalpy. Okay, when the chapter 7, the enthalpy is like we're looking at in general, right? And now in chapter 8 is more specific, like you have the table B2, B8, B11, and etc. And now in chapter 9, we are looking at the heat of reactions. Okay, but let me go through these questions. Okay, let me go through this question for you. So we start with, let me go to the new page. So first is, let me just write the reactions. This is the heptane. This is the toluene. And the byproduct is the hydrogen. Okay, oh, too far. All right. Let's say we have this coil to see that we have the heat, and the flowchart begins with the heptane that goes in, taking the basis 1 mole, okay, and then the product will be also 1 mole of the toluene and 4 mole of the hydrogen, and it's the same temperature, isothermal. Okay. That's number A. Number B, we need to take the reference, choose the reference, and of course, if not necessarily information given, we just assume that the reaction will be on the temperature, room temperature. Okay. So substance, the mole inside, specific enthalpy, the mole outside, and then specific enthalpy that is outside. Substance, we have 3 substances, not really that complicated, right? So I hope you can follow this. Okay, since there are no other substance other than heptane at the beginning, so we just have that as our reference, and it goes to completion, so nothing left here, and it is 1, 4, H2, H3. I think nothing wrong with this, right? It's just a usual table, and we are going to evaluate the H1. how do we need how do we calculate? First, we need to know the standard of the heat of formations, okay, of this heptane, and then because our reference is at 25, so we need to increase until 400 and use the CP. And remember, the CP is, we already have, right? We already have that the CP is given by 0.2427, right? I think this is pretty much easy calculations, not really that complicated. And we follow from the table, from the CP that we have in the information, this is resulting negative 96.8 kilojoule per mole. Need to be careful, okay? You need to be also correct for the signs, okay? So careful. Or if not, then you need to understand, okay, what's the meaning behind of this number, okay? Now the H2, this is the toluene, same thing with the first one, but now it's for the toluene. And also taking the CPDT, but now we are having the table B2, right, for the CP. Taking some calculations, and we are end up with the 110.2 kilojoule per mole. Okay. And then H3 for the hydrogen. I think the hydrogen, like for several gases that is in its elemental forms, we can get, this is directly from table B8. So this is comes from table B8 at 400 degrees Celsius, right? So I think pretty obvious. So, and then the heat, we can take this as equal with the delta H, which is the difference between the enthalpy out and enthalpy in. Okay, and this will be 110. Or let me just giving you the idea. The outside is H2 plus H3 minus H1, okay, and then multiply with its mole, and we got 251 kilojoule, and it's supposed to transfer to reactor because it's positive. And then number D is finding the heat, okay, heat of reactions. So heat of reactions at 400 degrees Celsius, we are getting at 25 kilojoule per 1 mole, okay? And I think it depends on how much moles they happen react with. Since it's just 1 mole, it's the same as what we have in the delta H, okay? So that's 9.14. So I hope you can also try the 9.15. It's pretty similar. The difference is it has the pressure. It has the pressure, and you need to assume it's ideal, and then you need to use this 2 liter to make out the mole. Okay, to make out the moles, and then the pressure we are going to have through the ideal gas formulations. Okay, so this is through ideal gas. So you need to check out by yourself. Okay, the rest is similar. You need to use the table, calculate the H. The enthalpy is pretty similar with the 14. Okay, so try number 15. Okay, so we look another questions. Let me check which one that is, I think, quite that is quite obvious and emphasizing. I think 20 or 22. I think it's too long and it's too much time needed. I believe we could go to 30. 31 or 32. I think we can try 32, although it's a little bit complicated, but let me try 32. Okay. So the Coke can be converted into CO by these reactions. Okay, these reactions, and it's contain 84% carbon by mass, and the balanced non-combustible ash. So it's not combustible, so not having any reactions. They are fed to the reactor. They have stoichiometric inequality for this carbon dioxide. The coke is fed at 75 Fahrenheit and carbon dioxide enters 400 Fahrenheit. Heat is transferred with this much amount, gaseous product and a solid reactor effluent. So this is ash and unburned carbon. They leave reactor at this temperature. Heat capacity is they giving 0.24. So we need to calculate the conversions. So how much the carbon converted into the product. Okay. Second question is asking the production of carbon monoxide. Okay. And yeah, this is just for knowledge. I will let you know. Okay, so we start with the writing the take basis of coke first. I think 100 is pretty much doable for our assumption. So we take the 84%, so 84 lbm for the mass. So the carbon, okay, the carbon will be 7 lb moles C fed, and it means that this will be 7 minus 7 lb, 7 the mass minus the moles of this CO2 fat. So in this schematic diagram, let me make it more clear. Okay. So 7 lb moles CO2 and 400 Fahrenheit, and then 7 lb moles, that is from 84 lbm carbon per hour, so 16 lbm ash per hour at 77 degree Fahrenheit. You have N1 and 2. This is lb moles CO and lb moles CO2, and this is 1830 Fahrenheit. It's also N3. This is for carbon per hour, and 16 lbm. So the ash, because it's unburned, is still 16. Okay. And the heat is this, right? Let me read one more time. Okay. Okay. So the because we have 100 mass coke, 100 coke, the carbon. So 84, heat is transferred. Okay. Okay, since this is 1, 1, 2, right? Okay, all right. The carbon is having 12, right? So that's why we have 7 Lb moles. Okay. Then we take the reactions. The heat of reactions for 77 Fahrenheit is the heat of combustions for the CO2 minus the heat of combustion for CO. So CO2 minus CO. So we can also look up the table. Okay, and this will be 74 210 BTU Lb mole. And let's say we have a fractional conversion. So X is a fractional conversion of carbon and CO2, that we will have the N1 is 7x, and then this will be 2 Lb moles CO from the stoichiometric and 1 Lb mole C that is reacted. It's supposed to be 14x, okay, 14x Lb moles CO, and N2 is 7, 1 minus x, the rest of it, right? Lb moles of CO2. N3 also the same. Because they both have the same moles, right? The same compositions. Now we take the reference. Okay, take reference C, CO2 and CO at 77 Fahrenheit, and CO2 at 400 Fahrenheit. We get from table B9, sorry, table B9. And then CO2, it raised up to 1830. This is also same, table B9. You can check, okay? You can check on the table by yourself, okay? Check whether this is correct or not. And again, the CO, we could check through same table B9. So this is the enthalpy, okay, the enthalpy. Let's say enthalpy 1, 2, 3. Okay. And for solid, this is all gases. So for all gases, for solid at 1800 Fahrenheit, we get the enthalpy is using the one that is given in the informations. Okay. And then multiply with the difference in the temperature. So enthalpy is 420. It's small because it is solid. Okay. The mass of solid, we are using the 7, 1 minus x, Lb moles C, multiply with 12 lbm divided by Lb mole plus 16 lbm. And this will be 100 minus 84x. LBM. And of course, before we have this, we can make out the table, or we can make the table now. Okay, from all this enthalpy that we get, we can take the table. So we have substance, CO2, CO, and the solids. The solid carbon, I mean. So we could try to write the enthalpy from the outlet and inlet. So this is 7, this is 100, this is 3000, this is 0, this is 7, 1 minus x, this is 20, 890, 14x, 13, 280, and this will be 100 minus 84x. Okay, from all this calculation here, and then we are going to look out for the x. Okay, x is the conversions. Okay, how much we are converting the coke into our product. Okay, we take the extent of reactions. Extent of reaction. This is we get from the mole of carbon monoxide so we have 14x, right, for carbon monoxide. 14x is equal to 2 extent of reactions based on stoichiometry, right? Stoichiometry. So the extent of reactions, is 7x. Okay. Now, from this extent of reactions, we are going to apply into our energy balance. Heat of reactions plus the difference in the enthalpy. So the heat is 5,85900, and this is 7x multiplied with 7421 BTU plus 7, 1 minus x, 2880 plus 14x multiplied with 13 and plus, I think it's too long. I make it too big. So make it a little bit left. And then 100 minus 84x. This is for solid, and minus 7 and 3130. And after solving this, we get the conversions is 0.801 or 18% conversion. Okay, so the second question is actually some logical question. So speculate on advantage and disadvantage of using the gas. So gas is more easy, right? So first, gas is easier to transport, right? To transport if you compare with the solids. But the CO at our case here is toxic. That's the disadvantage. Okay, I think that's quite logical. Okay, another example that I can show you. I think number 50. Okay, number 50. it's about the higher heating value. Okay, I haven't discussed much in the class, but let me just telling you through some calculations. Okay, so you have a fuel gas. It has methane, ethane, and carbon monoxide. The sample of the gas is charged to this vessel, 2 liter, at 25 Celsius, and we have this pressure, millimeter HE pressure. So the vessel is weighed before and after being charged. The mass difference is found to be 4.929 gram. The higher heating value is determined in calorimeter, and this is the value. Calculate the molar composition. So we would like to know the compositions on the gas. Okay, how much mole of the methane, ethane, and CO. So the ratio between these three. Okay, let's say we start with the reaction. So we have this methane, ethane, and the carbon monoxide. So let's take all the reactions. Take with the oxygens. Remember, the combustions, they need to have the product water or carbon dioxide. Okay. And you need to check whether it's stoichiometric. I think it's stoichiometric, right? Okay, now the higher heating value for each one of this. We also can check through the table B1 and take the negative of the delta of the heat of combustions. Okay, so we have 890.36 kilojoule per mole. This second one is 155.9. This third one is 282.99. And what we have in the question is we have 2 liters, right? So we have 2 liters. So let me write initial moles. We need to know initial moles through the 2 liters. So of course, ideal gas. Okay. So we can calculate the moles from the liters. So 2 liters. Calculate with the difference in temperature. Because we have at the room temperature, and then we have the pressure, and convert with 760 and divide with 22.4 liters. Okay. And we get that this is going to be 0.25 mole. Don't forget, we need to take the molecular weight, because we know the gram, right? We know the gram. The gram is, the difference is 4.929 gram. So let's divide with the mole. This will be brings to this molecular weight. Okay, now let's say we have the fraction 1 is the mole CH4 per mole total. X2 is mole ethane per mole total. And X3 is 1 minus X1 minus X2 mole CO per mole total. Okay, let's say we have the molecular weight is 19.72. So X1 for methane, we have molecular weight 16.04 gram per mole CH4. Okay, for this the methane. And then plus for X2 we have 30.07 for the ethane. And then we have 1 minus x1 minus x2 for carbon monoxide is 2801. Okay. Now the total need to be equal with the molecular weight. So the molecular weight, the compositions is, we have the each fractions, okay? Each fraction from methane, ether, and carbon monoxide. Now the higher heating value, we have 963.7 kilojoule per mole. So this should be equal to fraction 1. We take all the information from the first one, the higher heating value. We take through these calculations. So we have two equations that you need to solve. Okay, after sometimes to solve this, I believe this is going to have solutions. Okay, you have to use some either substitution or eliminations. Okay, and then you will get fraction 1 is 0.725 mole CH4 per mole total, and x2 is 0.188 mole C2H6 ethane per mole total, and x3 1 minus x1 x2, this is 0.087 mole carbon monoxide per mole total, and that's it. This is the one that we are looking for. Okay, I think I would just stop until here. If you have any trouble for the practice, okay, please let me know. You can also check the other one here. I think you can check this too, okay, number 55 and 56, okay, and also I think the last one, the 66 here, okay. I will give you also this selected problems for your reference, okay, and for the finals, okay, I hope, because I'm not sure what's happening in quiz chapter 8, okay, so actually because I didn't set up the security system in the platform, I think someone accessed the platform using the fake ID, and I believe this this activity is he or she tried to look out the questions, listing the questions, and try to solve, and then later he or she enter and then using her real ID and with answers, okay. So that's why I suspend the quiz for a while, okay. So I hope, okay, in the final exam, because I give you opportunity, open notes, open books, right, you can use calculator, I hope you are working the test by yourself, okay. So I believe you can prepare, okay. What I want you to prepare, okay, my suggestions, you can prepare the appendix, okay, the appendix in your textbook to help you organize, okay. Actually it's up to you, but my preference and my suggestions is you prepare maybe A4 paper, the blank one for calculations, and also your notes, okay. So you can summarize chapter 7, chapter 8, chapter 9. You can summarize into maybe 1 or 2 paper, okay. Notes maybe 1 or 2 A4, okay, paper. This is to help you to look on the summary, okay. And of course, if you have the textbook, you can prepare textbook. And for the appendix, especially the table, I think you can make a copy to help you to at least to prepare. Okay, if you just using one textbook for all, maybe you will feel disorganized. Okay, this is just my suggestions. Okay, so first is appendix, and of course don't forget to use calculator. Okay, of course you can use devices on your iPad, on your phone, but my preference is always using the manual way through calculator. It's much more reliable. Okay, if you use device, the digital device, sometimes it's not really reliable in my experience, but if you feel that it's way to go, then it's okay. Okay? But uh, my suggestion is just to prepare your calculator. Okay, so appendix prepare, of course the whole textbook if you have 3, and 4 is maybe A4 paper, several papers. Okay, some for some blanks for your test, and also the blank one also for calculations, because I believe some of you, for example, you take A4 paper, you need to make sure one paper, or at least one or two, is really official for your submission. So this is submissions, so you can take photo or scan the paper, and the other paper you can write this like all calculations, like messy calculations and all here. Okay, so you can make this paper on the left much more neat, clean, and easy to be recognized. Okay, if I cannot read your writing and you keep asking me why this, why that, because I cannot read your writing. Okay, so please make sure make this submissions paper clean, neat, and readable. Okay, so make sure it's clean, neat, and readable. Okay, so that is from me, and okay, I hope we can see each other again on the final exam. Okay, see you, bye.